Okay, chemistry, we're on to day 51A, electromagnetic waves. This is due on Wednesday. I'm getting this answers video out on Sunday night. You have a few days to do this, and we'll spend some time in class on this. All right, this is a challenging assignment, but just keep in mind it only deals with 3 equations. One is the electromagnetic wave speed equation, which says that the speed of light equals the wave speed of a wave times its frequency. So these two numbers multiplied together have to equal a constant. It's this. We're going to call this 3 times 10 to the 8th meters per second. So if the wavelength gets longer, the frequency gets smaller, shorter, or less, smaller. And if the wavelength gets shorter, very short, then the frequency gets higher. It's a much higher frequency. Now this equation relates the frequency to the energy in a photon. That's one of those little packets of light. Okay, so it's a photon. So this relates what's called the wave nature of light with the particle nature of light. So light travels in waves like this. That's a transverse wave, electromagnetic wave. But there's also times when it's better thought of as a little packet of energy called a photon. So the way you reconcile these two, don't try to reconcile them two at the same time. Sometimes you treat it like a packet, sometimes you treat it like a wave, but this equation relates the two because frequency is part of the wave. It's how many cycles it goes through every second, and NE of a photon is, this treats it as a packet, the energy of a single photon. Similarly, you have an equation. When you put these two equations together, you get this equation. So you can get the energy of a photon in one photon and how that relates to the wavelength of the light. Again, wavelength is a characteristic of the wave nature of light, right? It's how far it is between crests. So if you know that, you can figure out how much energy is in one of these little packets called a photon, all right? So we're only going to use these. We're not going to use any of these equations over here. So let's go ahead and get started. And you just have to get used to doing these problems and they'll come through to you. Now, I reprinted your assignment so I have more space to work with. I would suggest you might want to use line paper or pick up a revised copy which has this much space. It's a lot of space because some of these problems can be a little bit long, okay? So here we go. So an FM radio station has a frequency. So frequency is the Greek letter nu. And it's 88.9 megahertz. Now, what a megahertz is, you can find in your packet on page 2, where it has a lot of different units of measure, but I actually gave it to you right here. Megahertz means a million, it's 10 to the 6th hertz. Okay, what is the wavelength? So you want to know what the wavelength is. So the way I often symbolize that is wavelength or something, whatever I'm looking for, equals question mark, okay? That's what we're looking for. Now, it looks like we're missing a number. We need something else, right? Well, we know that it's an electromagnetic wave, so the speed of light is 3 times 10 to the 8 meters per second, okay? All right, so the wave speed for an electromagnetic wave is C equals lambda nu. Now, you should have the algebra skills. You need to solve for lambda because that's what we're looking for to do this. Okay, I'm going to come way over to the side and do this. But this should not be, if you have problems with algebra of this type, please come see me because you really need to know how to do this. So to get to lambda, you need to divide both sides by nu. These two cancel and you solve for lambda. Solving for a variable means you get it all by itself on one side of the equal sign. So it's C over nu. So I'm going to come over here, lambda equals c, the speed of light, over nu, which is 88.9 times 10 to the 6th. And I'm going to call it 1 over seconds. That's an alternate way to say hertz. You saw that in the previous lesson. So that means seconds in the numerator bottom and in the denominator bottom cancel, and you end up with meters, and that's the appropriate measure for lambda. Now, we learned how to do scientific notation kind of a manual way. So 3 divided by 88.9 and then 8 minus 6. But you should learn to just do it on a calculator. So we're going to take parenthesis 3 times 10 caret 8, close parenthesis, that's the C, divided by, and now you want to open another parenthesis, 88.9 times 10 caret 6, close the parenthesis, and that gives us we're just going to round it to 3.4. So lambda equals 3.4 meters. Okay? And it says also in nanometers, because oftentimes we express these in nanometers, billionths of a meter, okay? Meters, what the heck? So 3.4 meters. Now there's 1 nanometer equals 10 to the minus 9th meters. So that's our equivalency, so we're going to put nanometer on top because that's what we want to end up with, over 10 to the minus 9th meters. So meters cancels with meters, and we end up with 3.4 divided by, do this here, divided by 10 caret negative 9, and that gives us that number, which is, it's 3.4 times 10, it's 3.4 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8, 9 times 10 to the 9th. Okay, so that's going to be that many nanometers. So it equals 3.4 times 10 to the 9th nanometers. Okay, and there that is. All right, wasn't really necessary to do that. Okay, here we go. 7b is exactly the same as A. It's asking for wavelength, and you do it exactly the same way. So I'm going to leave that one to you. I'm going to go down to 8a. Violet light has a wavelength of about 410 nanometers. So again, a nanometer is 1/1 billionth of a meter. Go to page 2 in your reference packet and you can find that out. So here we go. It says wavelength lambda equals 410 times 10 to the minus 9 meters. Okay, so the nanometer, we get rid of the nano and we leave the meter, and it's 10 to the minus 9. So again, that's on page 2 of your packet. All right, it says, what is the frequency? Well, we know they want to know nu, and we know the speed of light. All right, so we have the wave speed equation. Okay, and I'm going to go ahead and solve for frequency. That's what we're looking for, and I trust you know how to do the algebra. If you don't, come see me. You're going to end up with frequency equals C over lambda. You divide both sides by lambda, okay? And that gets you to that. So that means frequency equals, okay, meters in the numerator top and denominator top cancel, so you end up with 1 over seconds, and that's the appropriate unit for frequency. So we're going to do this on the calculator again. I'll show you a few of these calculations. I won't do it all the time. So it's 3 times 10 to the 8th. So I'm going to open a parenthesis. 3 times 10 caret 8, close the parenthesis, divided by 410 times 10 to the minus 9th, open a parenthesis, times 10 caret negative 9, close the parenthesis, and we get 7.3 times 10 to the 14th for the frequency. And that's 1 over seconds or hertz. Either way you want to say that, okay? All right, so what is the frequency? Okay, we got that. Now calculate the energy of 1 photon of violet light. Okay, well, we got 2 formulas to do that. We were given the wavelength of 410 nanometers, so we could use this formula. That's the energy of a photon, Planck's constant times speed of light over the wavelength, or we just calculated the frequency. Let's go ahead and do that. It's fewer numbers involved. So energy of a photon equals Planck's constant times frequency. I'm going to come way over here. It's the energy in a single photon of light. Planck's constant. And the units for Planck's constant is joules times seconds. And then frequency here is the number we just calculated. Close parenthesis. You got seconds in on the top and seconds on the bottom, so the only unit left is joules, and that's what you want for energy. So again, I already have this number on my calculator, I didn't round it, but I have that same number. I'm going to multiply that by Planck's constant. And we get 4.8 times 10 to the negative 19th. That's the way the TI-30s show an exponent, negative 19. So and that's a typical number, 10 to the minus 19th, that you'll get for the energy in a photon of light. And it's joules. Okay? Calculate the energy of one photon. What is the energy in 1 mole of violet photons? So you can take this, the energy of a photon, and multiply it by a mole. And the unit is actually joules per photon times a mole, 6.022 times 10 to the 23rd, okay? And that's going to be photons per mole. Anything per mole is that number, okay? That's a mole of anything, but we're interested in photons because our units are going to cancel, so we end up with joules per mole in a mole of photons. So I'm going to take that number and I'm going to multiply it by a mole, 6.022 times 10 23rd, and we get 291,964 joules. Joules per mole, or if kilojoules, we divide that by 1,000. I'm not going to do that calculation on the calculator. I'll just do it, and I'm just going to round it to 291 kilojoules per mole of photons of that particular light. Okay, so that's how you do that problem. So let's review. So you were given a wavelength. You're asked to find the frequency. You know the speed of light. So you just solve the wave speed equation for frequency and you come up with that number. Then it says calculate the energy in 1 mole. So the first equation, the one we just used, was this one. Now the energy in 1 mole of photon, or excuse me, in 1 photon is that frequency we just calculated times Planck's constant. So there it is right there for 1 photon. And then if we want to know a mole of photons, we simply have to take that number and multiply it by a mole, 6.022 times 10 to the 23rd, and we end up with this many joules in a mole of photons of violet light, or this many, roughly this many kilojoules. I rounded it off. Okay? All right, let's keep going. So you're going to do 8B. Now I kind of lied here. I said violet. I didn't change the color, but I changed the number. Violet has a very specific wavelength, and I just went ahead. It doesn't matter. We're practicing working the problems here. Okay. 9A. The energy in a mole of photons of red light from a laser is 175 kilojoules per mole. Okay, so energy of a mole, and this time we're talking about red. And I'm going to change that into joules. How do I do that? I just add 3 zeros. 175,000. I could do the formal conversion for you, but it's if this is 1,000 joules, then it's 1,000 times that much. So that's joules per mole. All right. And it says calculate the energy of 1 photon of red light. So there's that much energy in a joule of, in a mole of red light. So in a single photon, there are, we're going to divide that by a mole, 6.022 times 10 to the 23rd photons per mole. Again, that number is true of anything per mole. That's what a mole is defined as, but we're interested in photons here. Photons per mole. So mole in numerator bottom and denominator bottom cancel, and you end up with joules per photon. That's what they're asking for. Calculate the energy of 1 photon of red light. So we're simply going to do this. I'm not showing you what I'm doing, but I'm just dividing these two numbers on my calculator. And I don't like that number. Okay, so let's show you how I calculate this. It's 175,000 divided by, now be careful, you can't just put 6.022 times 10 to the 23rd. You got to put it in parentheses. And I just always get used to putting things in parentheses. 6.022 times 10 caret 23, close the parenthesis, and that gives us, again, a 10 to the minus 19 number, which is typical energy in a photon of light, and that's joules per photon. Okay, and that's what it asks. Calculate the energy of 1 photon of red light. What is the wavelength of the red light in meters? Okay, so now what equation do we use? We only have 3 to work with. So it wants wavelength, so we know the energy of photon. These two numbers are constant, so we're going to do this. So we're going to write this equation down. And it wants to know this. So to do your algebra, I don't want to get bogged down in algebra. You multiply both sides by lambda, this thing. It cancels on the right. It ends up over on the left here. Then you divide both sides by energy, E there, and divide E there. You cancel this side. And what you're going to end up with is this. If you don't understand the algebra, come in and I will help you with that. All right? But I want to focus on the chemistry here. Okay? So that's what you would end up with. Okay, so we come on down here. And then this was the energy in joules. So seconds cancels with seconds, joules cancels with joules, and what I end up with is meters here. So I'm going to multiply this times this divided by this. Okay, now I'm going to multiply this times this divided by this. Again, I'll show you one more time because it can be a little tricky. Clear my calculator. 6, whoops, I'm going to actually start with a parenthesis. I'm going to close the parenthesis, times the speed of light, and I need to open a parenthesis again. And now I'm going to divide it by this number down here, open a parenthesis, and I get this, so 1, 2, 3, 4, 5, 6, 7. 6.85 times 10 to the 7th, and that's in meters. So what is it in nanometers? So I'm going to take that number, and there is 1 nanometer for every 10 to the minus 9 meters. Meters cancel, so 6.85 times 10 to the 7th divided by 10 to the 9th. And it gives us 685 nanometers. Okay, there you go. All right. Okay, so now it's asking us, compare the energy of the photons of the violet light and the red light. So the violet light, and the actual wavelength for violet light is in 8A, not 8B. I just gave you a number to work with that was different. But it's 410 nanometers for violet. And the lambda, the wavelength for red, is 600. It's what we got here, which is 685 nanometers. Okay, so the shorter the wavelength, the higher the frequency. This is a shorter wavelength than this, so it's a higher frequency, so this is more energy. And this is less energy. And if you look at the electromagnetic spectrum, red is the lowest energy type of visible light, whereas violet is near the very top of energy. So again, shorter wavelength, higher frequency. Longer wavelength, lower frequency. So this is less energy. Okay? And by what factor, don't worry about that part. Okay? All right, so that takes care of that. You do 9B. Okay, the most prominent line in the spectrum of neon is found at 865. Other lines are found at 837, 878, 878, and 1885. Which of these lines represents the most energetic? So again, shorter wavelength, higher frequency. Let's just write that down. Okay, so higher frequency, which equals more energy. So just learn that relationship. Again, it's in one of the first two lessons there. We talk about that. Okay, so the shorter wavelength, 865, 837, looks like it's the shortest. So this one. Okay, that's the most energetic light. It's the shortest wavelength. That's all you need to do for that one. All right. Okay, B. What is the frequency? I'll leave that one to you. You have a wavelength. Speed of light equals wavelength times frequency. So what is the frequency? You have to solve for that. C over lambda equals frequency. Plug in the numbers. What is the energy of one photon of this? So we've already done one like that. So once you have that wavelength, you can use, so for the first part of this question, you use this. And for what is the energy of one photon at this wavelength? There you go. So the energy, you have the wavelength, you have H and C, those are constants. Plug in the numbers and come up with E for that. Okay, so I'm going to leave that one for you to do. All right? You want me to say that again? What is the frequency of the most prominent line? So this is a wavelength. It's in nanometers. It's that number. So that number goes into wavelength. C is 3 times 10 to the 8. So you're going to solve for V, and that'll give you the frequency. What is the energy of a photon at this wavelength? So you take that wavelength, you plug it into this equation right there, 837. H is Planck's constant right there. C is speed of light right there. You just plug in the numbers and do the math. The hardest part is, manipulating the calculator and not making a mistake. All right? Okay. What series represents visible light, and what orbital do the electrons fall from in that series? That's called the Balmer series. And I'm going to leave the second part of that question to you. You got to watch the instruction video, the day 51A instruction video, okay? Let me get that on screen there. What series represents visible light, and what orbital do the electrons fall from? So it's called the Balmer series. That's the one for visible light. You look up the rest of the answer to that question, okay? Again, I'm generally grading you on the things that I don't give you, because anybody can copy. So be sure you get those. Okay. Express the following in nanometers. I'll do the first one. So I should have put what the units are here. These are meters. Otherwise, you don't know what to do. So it's 2. We already did some of these just like this. 2.98 times 10 to the minus 7 meters. And there is your equivalency is there's 1 nanometer equals 10 to the minus 9 meters. So you're going to put nanometers on top and put meters on bottom. Meters cancels and cancels. And if you do that, you end up with 298 nanometers. Okay, now you do it for this one. All right. List the 7 different colors of light in the spectrum from highest energy to lowest. On the highest energy on the left to lowest energy on the right. Also identify which end of the spectrum has the highest and lowest frequency, and which end has the longest and shortest wavelength. So just go and view the part of the video on the electromagnetic spectrum where all the colors are and answer that question, okay? So this is the Roy G. Biv. So go to that, okay? 5. A bright beam of red light, lower energy, is not able to remove an electron from an atom, but a beam of blue light, higher energy, that is not as bright can remove the electron. Explain why the bright light cannot do what the dim light can do. Okay. This actually wasn't in the video, so this is going to be a little bit of a teaching moment. Actually, I'm going to do this separately, so I won't do it here, because not everybody's going to watch this video. So let's skip that one. Okay. What series represents electrons in hydrogen falling to the second orbital? Okay, that's in the Day 51A video. What color light is produced when an electron in a hydrogen atom falls between each of the following, from the third to the second, from the fourth to the second, and so on? What color is that? That's in hydrogen. Okay, that's in the video. Which of these colors has the highest and which has the lowest energy? I'm kind of asking some of the same questions over and over, but it's important that you understand these relationships with color and the light and electromagnetic waves. What is the order of the colors of light from? Well, that's kind of asking the same question as, I think, question number 4, but that's okay. Answer it again, seriously. Just write them out. You don't have to give me complete sentences, okay? What series deals with electrons, hydrogen falling to the first orbital? Okay, that question hasn't been asked yet. That's in the video. What series deals with electrons in a hydrogen atom falling to the third orbital? That's in the video. Watch it. And name 6 types of electromagnetic waves on the spectrum from lowest to highest. Just go to the electromagnetic spectrum, the part of the video, and you can answer that very easily. Okay, that takes care of this. If you need help, I have tutoring almost every day after school and before school, so come in and see me.